So far, we've studied the three data structures. We have studied linked lists, okay? We have studied stacks, and we have studied queues. All right. For each one of them, we had some operations which were common between them. For example, insert. Okay, insert and linked list. In a stack, it was called push. In a queue, it was called enqueue. For remove, we had pop, and here we had dequeue. Okay, for search, in a stack, we had the top method. In queue, it was called first or front. Okay, we also had the isEmpty, and we had the size. I think this was common between all of them. So if I want to create a table like this, and I want to see what was the runtime for each one of them. Okay, so let's try to insert something in a linked list. What was the best way, what's the fastest possible way of inserting something in the linked list? What was the runtime for that?
Beginning.
Insert in the beginning.
Very good. We always try to insert in the beginning. Okay, so my best case was O of 1. O of 1 means constant. It takes just constant time because inserting in the beginning is taking a very small time. If you have to scroll down all the way until the end of the list, and imagining the size of the list is n, okay, in that case, the runtime would be big O of n. Okay, so what was the worst case scenario? Worst case.
Middle.
In the middle.
At the end. Imagine you don't have the tail in the linked list or a single linked list, and we decide to insert something at the end. So you have to scroll all the way until the end of the list. Imagine this is your list. Okay, and you have many nodes. And this is the nth one. So imagine you like to insert something after this. So we start from the beginning, scroll all the way until the end. So it's going to take n times, okay, or big O of n. Oh yeah, if you want to remove something from the linked list, what's the best case?
Constant.
Imagine we want to remove the first element.
It's the end at the top, which is the tail.
Okay, if it is the first element, the runtime would be constant. You got lucky. Okay, but the worst case scenario is, imagine what you're looking for is not there.
In the middle,
It's not in the list. So we go and search all the way until the end. We didn't find it. And at the end, we say we were not able to remove something. So it's going to take O of n times because we're going to search n times. Okay, for searching, we're searching something. I think it's going to be similar to remove, right? So imagine something that we were searching for was the first node. So in this case, the runtime would be constant. We were able to get it only just in the first search. Okay, and the worst case would be we go off n. Imagine what you're looking for is not in the list. So we go all the way until the end. We were not able to find it. So the runtime would be big O of n. Okay, what about isEmpty? What's the big O for this?
And doctor?
Because we will check the head only.
One.
Very good. We don't have to go and check all the list. We simply see if the head is null or if size is 0. So in both cases, it's going to be O of 1, just constant time. Okay, how about size?
Also 1, because it will retain all the size.
Also 1. See, we always recommend it to have the size variable. Like if size variable is there, we're always changing it. Every time we insert something, we increment it. Every time we move something, we decrement it. So if you're maintaining the size variable, the runtime would be constant. Okay, you simply go and check the value and return this value, and that's it. All right. So Remember, big O notation is always talking about the best case or the worst case.
Worst case.
Worst.
Worst.
We're always looking at the worst case scenario. So we're not going to consider this, okay? This is just to explain. All right. What about the stack? If you like to push something in the stack, what's the runtime?
O of 1.
O of 1.
O of 1. Very good, because we push on the top. Okay.
Yes.
If I've implemented the stack using a list, we simply go and insert in the beginning of the node. All right. How about pop?
Same thing, O of 1.
All of them are O of 1.
O of 1, constant time. Okay. Top.
O of 1.
O of 1. All right. How about is empty?
O of
The
1.
same O of 1.
O of 1. How about size?
O of
O
1.
of 1.
So that's also constant. So
Yes.
can I say that stack is faster than linked list?
Yes.
Yeah, but can stack do everything that a linked list can do?
No.
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 No. Okay. How about Q?
O of 1
Okay.
as well.
O of 1. DQ.
O of 1.
No.
Front
O
of
of 1.
constant. 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 It's similar to stack. Okay. So overall, if I want to summarize, look at the worst of all of these operations. The linked list is big O of n. Stack is constant, and Q is constant. But remember, stack and Q cannot do what the linked list does, especially with the search. Okay, like if you want to, if somebody asks you to search something in the queue, and after you search, you have to return it back into the original position. In that case, the runtime would be. Come on, you studied this yesterday.
And
O
two
of
and one.
O of 2n.
Yes,
Okay.
because
Same goes here. O of 2n. So this is even worse than
the
the
search
linked
for the
list.
linked list. Yes.
All right. So if you want to have a data structure that allows you to search, it's recommended not to use the stack or the queue. They're really bad for it. All right. So this is summary of the 3 data structures that we have studied. Now today we're going to look at another data structure, which is trees. Okay. We're hoping to find a time which is faster than big O of n. We're looking for something better than, okay, less than times something that will take less than linear time, O of n. So before we begin, trees is a very big topic. Okay, trees is a very big topic. So before I actually go and start talking about it, I'll just give you an estimate. The runtime for trees is big O of n. Okay, it's no better than linked list. But then we go into a kind of a tree, which is called binary tree. Are you familiar with this diagram? I think we call this thing Venn diagram. Okay, the runtime for binary tree is big O of n, but it's faster than tree. A kind of binary tree is something called a binary search tree, BST. Okay, most of the time, the runtime for BST is big O of log of n, but sometimes it can be big O of n. But remember, for big O, we're always considering the worst case scenario. So we don't look at this. We only say that worst case scenario for BST is big O of n. It doesn't still solve our problem. So we have another
Doctor, what's BST?
binary search tree. We'll talk about it
okay.
inshallah next week. Okay, so a kind of a binary search tree is an AVL tree. Okay, AVL is a short for names for the people who invented it. So AVL is guaranteed to give you O of log of n time. Okay, so remember, this is guaranteeing log of n time. Is this faster than big O of n?
Yeah, much faster.
Much faster. Okay, binary search tree most of the time gives you log of n, but sometimes it can give you O of n. Like we're always studying big O notation. Big O always looks at the worst case scenario, so we have to consider big O of n. Binary tree sometimes gives you log of n, sometimes gives you O of n. Okay, so again, since we're talking about big O, so that's going to be big O of n. And trees almost always give you O of n, big O of n. So the goal is to study AVL trees. Okay, AVL trees guarantee a faster runtime. But to study AVL, we have to study BST. To study BST, we have to study binary trees. To study binary trees, we have to study the tree data structure. Okay, hence the time. It usually takes between 3 to 4 weeks to cover these topics. All right, is this clear? Shall we move on? So today, my goal is to talk about trees. Okay, we'll see how trees work, how do we implement them, and then we're going to move into binary trees. So far, so good?
Yes. Dr. AVL is a company?
No, it's the name. It's the name of the people who invented it. It's a short for that.
Oh, okay.
I'll talk about it later.
Is it for all languages or like most languages?
No, it's English.
I mean, like Java or like Python. Like,
Oh, wait. Yeah,
language
see,
is implemented?
okay, what we're studying, data structures are concepts. They're not bound to a language, a particular language.
Oh, we're supposed. Okay, so it's like.
Yeah. So yeah, think about everything that we're studying in this course does not only apply to Java. You can apply to almost any programming language.
Yes. Okay.
Okay.
But Doctor, obviously, like the tree data structure doesn't look like a circle, right?
No, it does not. No, this is just a diagram. I think we call
Yeah.
it the Venn diagram.
Well, you should do a square around it.
Okay, I'll try to show you why is it called a tree. Okay, so trees, what we're hoping for, okay, we're hoping for a runtime that's going to give us log of n, okay? Do you remember any algorithm that we studied before where the
Yes.
runtime was log of n?
It decreased. It's like the opposite of exponential. So.
And the recording of the binary search in the array.
Very good. So binary search gave you a runtime, okay, which was binary search, okay, which was log of n. The opposite of log was
Exponential.
exponential. What was the algorithm that we looked at? We looked at only one example for each one of them.
I think prefix averages. Oh, no.
No, it was Fibonacci numbers.
Yeah. Fibonacci.
Okay, Fibonacci numbers. So how did we estimate that this was a log of n? So when we said that if we have a large array, okay, so in the first iteration, we're able to half the space, search space or execution space, and then in the next iteration we half it further, and the next iteration we half it further until we find the element. So we're getting a shape kind of like this, an upside down triangle. Okay, so here if we had 16 operations, that becomes 8, and then 4, and then 2, and then 1. Okay, we're going to get something which is big O of log of n. The Fibonacci numbers was opposite. Okay, so we had one formula. In the next iteration, it became double. The next iteration, it became 4. Okay, and so on. So we had 1, we had 2, 4, 8, 16, and so on. So the shape kind of looked like this. Okay, a triangle pointed side up. Okay, so this is increasing. This is increasing. So if we had something like this, which is increasing twice every time, we said this is exponential. And if it was halving every time, this is log of n. Okay, so we're hoping for implementing something that kind of looks like this. Okay.
So Dr. Trees could be exponential or logarithmic?
No, again, I mean, this is just a shape. I'm just trying to explain. That's what we're hoping for. We want to have something like this. So again, now we're going to look at some rules and regulations about trees. Okay, naturally in real life, if you look at a tree, okay, tree usually has just one stem, and from here it grows up. Okay, there's branches and further branches and branches on branches, and there's leaves on the branches and so on. So we're expanding this way. If you flip it upside down, okay, you're going to have something like this. Okay, and then you have branches, and then branches, and then branches, and then leaves at the end. Okay, so this thing is called the root, and we have these things which are called branches. Okay, and we have these things called leaves. Leaf one, leaf many leaves. Okay, so what we can do is we can implement a tree that kind of looks like this. If you look at this tree, it's giving you this kind of shape. Okay, it's giving you this kind of shape. So I've basically flipped it. Okay, so if I start searching this way, and if I go only in one direction, okay, I'm hoping the runtime would be of log of n. All right. So later on, we're going to see how do we achieve this. Okay, so far so good. Any questions?
No, thank you.
Okay, so let's go to the slides now. All right, so what you see in front of you is a tree. Okay, so there's some kind of relationship between the top node. Okay, so it's a mammal. All of these animals are mammals. There's lots of applications for trees in computer science. Think of this. Computers are us. Okay, it's a company. They have different divisions. They have sales, manufacturing, research and development. We have two departments for sales. We have sales within US. We have sales in international market. In international market, we have sub-offices. We have an office in Europe, in Asia, in Canada. Manufacturing, we manufacture laptops, we manufacture desktops. So what you see over here is a hierarchical representation of the different departments and sections within a company. Okay, we can safely say that this is a tree. All right, can you create a similar kind of structure for Prince Sultan University? Anyone?
Yes, we can divide the Prince Sultan into students, college professors, then faculty, and so on.
So we have PSU, we have academics, okay, and we have administration. Under academics, we have colleges. So we have CCIS, we have engineering, okay, we have women campus, and so on. Under CCIS, we have departments. We have computer science, we have information systems. Under CS, there are students who study CS program, IS program, sorry, SE program. Under IS, there is an IS program, and so on. So each of the colleges is going to have something like this. So this is a hierarchy, and this shape looks like a tree. Okay. Now let's look at some rules and definitions. What you see on the right side is a tree. Like I told you, the top part is going to be only one element. It's like the head in a linked list. Here we don't call it head, we call it the root. Okay, a root. So a tree has one root. There can be many children to this root. So I can call this thing a parent and also a root. All the nodes which are connected to the root are its children. Children can have other children. So for example, B, okay, B, node B is a child of A. Node B is a parent to E and F. Same goes with F. F is a parent to I, J, and K, but F is a child to node B. So we can follow the same structure. We can say B is a parent of F. B is a grandparent of I. Similarly, I is a child of F. I is a grandchild of B. Can I also say that I is a grandchild of A?
Yes.
Yes. So this goes with the levels. Okay, the more levels, the more grander it becomes. Okay. If you look at this side, we also say that a tree can be inside another tree. For example, C, G, and H. This is a tree. We can say this is a subtree of the tree whose root is A. Okay? So if you want to look at this triangle, it's showing you C is a root of this subtree. C is a parent to G and H. But at the same time, C is within the bigger tree, which is starting at A, rooted at A. So C's parent would be A, and A's child would be C. Same goes with D. Okay, so far so good? All right, some of the definitions. So we have the nodes which do not have any children. For example, E. So the nodes which do not have any children, they're considered leaves. Okay, leaf of a tree. So easily the node that does not have any children. So here, if you look at this tree, which nodes are leaves?
A and I and J, K, D, H, D.
So I have E, I, J, K, G, H, and D. All of these are leaves. Right. The other nodes, they're all called internal nodes. For example, A, B, F, C. Okay, these nodes are internal nodes. Right. If this is clear, let's move on. All right. We also have some other measures. Usually this is the depth or the height of a tree. Okay, so if you look at this particular tree, what we're going to do is we're going to start at the root. We're going to start at the root, start counting from here, and go to the longest branch. So as it happens, if I go towards B, starting from A, go to B, and from B to F, and then from F to any of these I, J, and K. This is going to give me the longest branch of the tree. So what we do is we count the levels. So A is level 1, B is level 2, F is level 3, and I is level 4. So this particular tree has a height of 4. Okay? This particular tree has a height of 4. If somebody says, what's the depth of a node? What's the depth of a node? So we have to provide the node. For example, what's the depth of node F? So what we do is we go upwards. Okay? So starting from here, we count the F. It has one parent, B, that's 2. It has a parent, A, that's 3. Okay, nothing before that. So the depth of F is 3. Okay? So be careful about this because a lot of people make mistakes here. So I'm going to rewrite this over here. So imagine I have some tree. Okay. Somebody asks you what's the height of the tree. So what we're going to do is start from the root, look for the longest branch, okay, and up to here. Now we count how many nodes are there. So this is 1, 2, 3, 4, 5. So height for this tree is 5. If somebody asks you what's the depth of this node, okay, so you have to provide the node. What's the depth of which node? So for this blue node, what's the depth? We're going to count 1, 2, 3. So depth for the blue node is 3. Okay, small quiz. Can somebody tell me the depth for the green node?
4.
4, Doctor.
Good,
4.
4. Okay, depth would be 4. All right. Now we need to remember a formula. What's the maximum number of nodes that you can store in a tree? What's the maximum number of nodes that you can store in a tree?
Height -1.
Okay, there's a formula for that. All right, and it works with binary trees only. Binary trees. Okay, which is 2 to the power height, okay, maximum possible height, -1. So in this particular tree, the height is 5, so it's going to become 2 to the power 5 -1, which is 32, -1 is 31. Okay, so what we're trying to say over here is the maximum number of nodes that you can put in this tree. Okay, you can look at all these imaginary ones which are not there. I cannot draw all of them here. Okay, but you get the idea. So if you count all of these, it's going to give you exactly 31. We're going to revisit this formula a bit later. Okay, this formula is important. It helps a lot. Okay. Fine. Now, how do we implement a tree? A tree. There's, again, we have two ways of doing this thing. We can implement this tree, we can store the tree in an array, or we can store the tree in a linked structure. Like if I try to store this thing in an array, that's a problem. Why?
Because if you want to add a new branch or leaf.
So here's my tree, here's my array. Okay, and here's some tree. Let's say I have 3, 2, 1, 4, 5, 6, 7, 8. Okay, let's say this is some tree. Okay, remember a tree has no limits to number of branches. In this particular tree, we have 4 branches for the root 3. We have 2 branches here. There's only 1 branch over here. But we can add more things. Okay. Now, how do we store this in a array like this? Should I simply go and put 3, 2, 5, 6, 1, 4? Or do you have to have some kind of order?
I think
Is
there's
it one array or is it more than an array?
That's just one array.
no. I think we have order.
We have to have some kind of order. It doesn't work this way. Okay. So
It will be 3, 2, 1.
what we
Then-
can do is we can suggest something. We'll store level by level. So we go with 3. Then we go with 2, 5, 6, and 7. And then we go with the next level, which is 1, 4, and so on. Okay? So far, so good. But now we need to remember which ones were which. Okay, how do we know that this is level 2, and this is level 3, and this is level 4? How do I know that 1 is not connected to 7? How can I be sure that 4 is not connected to 5? Okay, so this is difficult.
Yeah, that's why you should do more than one array.
It's hard to do it like this. So one of the solution is, hey, why don't we have multiple levels of arrays? I can have 3.
Yes.
I can have another array which is going to store 2, 5, 6, and 7. And then I have another one which stores 1, 4, 8, 9, and 10. But now the question is, how can we connect them together? We have 3 arrays, A1, A2, A3. So how do I know that 4 is connected to 2? How do I know that?
So we have to create another array that encompasses the 2 arrays together.
This is becoming complicated.
Yeah.
Okay, that's making our life harder. Again, remember, the whole reason that we're studying trees is because we think linked list is not a good solution. All right?
Mm.
Linked list runtime is big O of n, and we're looking for something which is easier to implement, which is not very complicated. But here, what we've seen is it's horrible.
Yes.
Yeah, it's runtime. We're not sure how to compute the runtime. We're not sure how to implement this thing. We're not sure how to implement the relationships. Like, here's a problem. Remember, in the linked list, you're allowed to insert and remove anything from anywhere you want.
Mm-hmm.
Like here, what if somebody says, hey, I want to insert something here? Now, what are we going to do? Does
You
that
have
mean
to.
that I have to create a new node over here and put 11 over here?
No.
So what about shifting? Yeah. So
Yeah, it takes a lot of time.
again, complicated. Okay, and we're not sure it's going to give you big O of n time. Maybe it's going to give you more time. So we're not happy with this.
So use a linked list.
So think about using a linked list. Okay, if I'm thinking about a linked list, I'll probably have, let's go with a tree.
Okay.
Okay, so imagine I have something like this.
Okay.
Of course, you can have some other nodes over here.
So
how can I
basically,
store this in a linked list?
it's just a linked list with branches, basically. So if you have, like for example, the first row, or like the first column after the root.
So I can say that there's a root. It's like a head in the linked list.
And
And
then
then from here, we're going to connect to 2.
yes, and then under the 2, we connect to 4 and 5 and 6.
3 and 4 and 5 and so on.
Mm-hmm.
Yeah.
And then the
when
2.
we connected with more than one number,
Yes.
2 and
the 2
3
is
and
connect.
Okay, now how can this be possible? We cannot do it like this.
Can we? Can't we?
No, we cannot. No. There's only one pointer, right? We have the dot next.
yes.
Mm.
How can one point to 4 different things? Like,
What if we have another pointer,
so
like
this
the
doesn't work.
doubly linked list? Because
But we don't know how many nodes could be there. There can be many more. We don't know how many.
So linked lists are not a good solution.
So even this one is not a very good solution. Okay, but what we can do is we can create something like this. We can say there's a root. Okay, and this maintains another linked list or an array.
Okay.
So we're gonna put 2, 3, and whatever number of nodes over here. And for each one of them, within it, we're going to store
Another
another
linked list? Ah, okay.
It's like linked list inside another one.
Mm-hmm. Yes, yes. So like a recursive, not recursive, but like
Okay,
a within.
like this.
Mm-hmm.
But do you think this is a good solution?
It could take a lot more time.
No, it isn't.
Yeah, it takes a lot of time.
Yeah, is this
More and more will be so complicated. Still complicated.
We're not sure it's going to give you
Not flexible.
time, and this is complicated. Okay, it's not easy. So what's the point of studying all of this data structure then? So this is telling you, okay, it works well. It works well. It may work only if your tree looks exactly like this.
Mm-hmm.
Okay, this is a tree, and somehow when I'm searching for something, I go only in one direction and I find it. Or if I'm trying to remove something, I go in one direction and find it. Only in this scenario, it's going to give me log of n time. Otherwise, it's almost always O of n. But we're not even sure about O of n. Maybe this is complicated.
More than
the way we saw it. It could be more than O of n. We don't know. We're not sure.
Mm.
Doctor, this way we can organize the data a lot better. Keep the bigger on the left or on the right. Some way.
Very good, very good. We're going to come to that. Now, in the book, they have given some kind of implementation for this. Okay, some kind of implementation is there. Right. So, but on the whole, it's not a very good idea. It's not a very good idea to implement a tree. Okay. So moving on, I'm going to get back to this topic, pre-ordered traversal. I'll get back to it. Moving on. So the next class is the binary trees. Okay. Let me scroll back to what I showed you before some time ago. This diagram. So far we've studied trees and we've said that they're complicated. They're not a very good solution. We're not sure if you can get something even in big O of n time. Like if this tree is giving you big O of n time and it's complicated, I would rather use a linked list. I know that its runtime is big O of n, and I can even make it faster. Right, now we're going to look at binary trees. Okay, binary trees. Like, what's a binary tree? So a binary tree is a tree with the following properties. Okay, each internal node has at most 2 children. Okay, at most 2 children. So previously there was no limit. Every node can have as many children as possible. Okay, this is a tree. But now we're restricting. We're saying, okay, we're not going to have more than 2. Maximum is 2. It can be 1 or it can be 0. Okay, so if you look at this particular node, there's 0 children. There's nothing here. This particular node has only 1 child. This node has 2 children. So for binary tree, okay, what's the property? Maximum 2 children. Sorry, I think I have to say less than. So less than or equal to 2 children per node, not more than that. Okay, what's the other condition? The children of a node are an ordered pair. There's some kind of relationship between the left and the right. Okay, but it's not exclusive. We call the children of an internal node left child and the right child. So if you look at this diagram, D is the left child of B. E is the right child of B. B is the left child of A. Okay, everything else, okay, all the things that we studied a bit earlier with the trees, they all apply recursively, perpetually. For example, okay, A is the root of the tree. E is a grandchild of A. I is a grandchild of A. The height of this tree is what?
4.
4. Remember height. You start from the root, you go to the longest branch. So it's either H or I. Both cases, it's 4. What's the depth of the tree at F?
3.
1, 2, 3. What's the depth of the tree at A?
1.
0.
1. No,
Or 1 is
1. Okay? So the same formulas, the same definitions apply over here. The only thing that we have added is the condition that a node may not have more than 2 children. It can have 0, 1, or at most 2 children. And the other thing is that the left child and right child are not defined. So there's a left child and the right child. Yes?
So, the children of a node are ordered pair. Does that mean they have to be sorted?
No, they don't have to be sorted. No.
Okay. So what does it mean to be ordered?
We'll study this thing for the next time. Okay? The next one is binary search tree. We'll study that tomorrow, inshallah. Okay. So binary search tree uses this property, but here we're not using this property. Okay, here are some real-time examples of binary trees. So in a computer, when you're evaluating expressions, okay, for example, something like this, 2 times A minus 1 plus 3 times B, we can represent this thing using a binary tree. So you can see this thing. This was a tree. The root of the tree is plus, okay, and it has 2 children, x, a multiplication, and then you have 3b over here. These are children of x. All right. So when the computer is evaluating expressions, it uses trees and stacks to evaluate expressions. So this is just an example, just to show you that we can represent an arithmetic expression tree as a binary tree. Another example, decision trees. Okay, I think the IS students will study this thing in detail later on. So decision trees are a very good way of finding a solution to a problem. I think also the computer science students, the software engineering students who take the AI course, artificial intelligence, they will also study this thing in depth. So a very simplistic decision tree. Want a fast meal? Yes, no. If you go to yes, then we ask a question, how about coffee? So yes, no. So you can go to Starbucks or Chipotle. If you go no, okay, on expense account, yes, you can go to Gracie's, no, go for Paracon. So this is just an example of a decision tree, which is binary tree. Like, why is this binary tree? Why are we saying this is binary tree?
Because it only has two options, or like two children at max.
Good. There's a maximum of only two options, yes or no. Now, remember one more definition. If you have a tree like this, okay, we call this thing a complete tree. All right, complete tree. Every node has exactly two children.
Okay. So does that mean it has O log of n because it's complete?
So this is going to give you exactly O of log of n time. And this is desirable. This is what we're trying to achieve.
Okay.
All right, these are some properties of binary trees. Again, we've studied all of those before. These are some formulas, but I think the most important one is the height, okay? Height. So you don't need to memorize any of these. The most important one is the maximum number of nodes given by the height, which is, you remember that? To the power height minus 1. So n equals to the power height minus 1. Okay. So again, this is the API or the ADT. We're going to define the left, right, okay, and how to work with that. Now, a few minutes ago, I told you I'm skipping a slide about the traversal. Okay, let's look at traversal and how this works. Now, this is very important. There's going to be a question about this in the exam and perhaps also the final exam. So pay attention. How we do traversals. Okay, so if you want to traverse this tree, remember when I'm traversing a linked list, we always start at the head. Okay,
Yeah,
and
then you
go
have to
next,
go all the
next,
way
next,
through.
next, next. So we have only one direction.
Yes.
Okay, here we don't have one direction, we have two directions. So which way to go? Should we go left? Should we go right? Okay, so we have to come up with an algorithm which is going to tell us to do this thing. So we have three algorithms. We have pre-order, okay, we have in order, and we have post order. These are the three popular algorithms that we use for traversal of a binary tree. Now, how does that work?
Pre-order the
Pre-order
left.
means that visit the node first. Okay, visit the node first, then go left, then go right. Okay?
Oh, okay.
Visit the node first, then go left,
Then go
then
right.
go right. In order means that first go left, then visit the node, then go right. Post order means first go left, then go right, then visit the node. Let's look at this example using this tree. So if I'm doing pre-order, I'm going to start always at the root. This is the root of the tree. We always start
So we
here.
go to 3 and then we go
So
left.
it's saying visit left, right. So we're going to visit 5, then we go left. Visit 3, then we
2.
go left. Visit 2, then we go left. There's no more left. Now you go right. There's no more right. So once you're done, okay, we did visit, VLR. We visited, there is no left, there is no right. So now we go back. If you remember here, it was VLR. We visited, we went left. Now we have to go right.
Mm-hmm.
So now we go to right, okay, which is 7. So we visit 7. There's no left, there's no right, so we go back. Now there's no more right. We're done with traversing this thing, so we go
So I
back.
go right.
Remember here we also had VLR, we visited, we went to the left. Now it's time to go to the right. So we go right, again we're going to have VLR. So we're going to visit 4 now. Okay, and then we go left. So VLR, so again visit 1. Okay, there's no left, there's no right. So now we go back. There's a right. So again we go here and we go visit 6. No left, no right. So go back. Okay, we're done with VLR. Go back. We're done with VLR and we're done. So this is called pre-order traversal, VLR for short.
Doctor,
Okay.
is it like the fastest going down? Like in order is faster than pre-order than post-orders?
No, all of them have the exact same runtime. There is no difference. It's just that,
Okay.
yeah, which way is better depends on the application. There's different kinds of applications.
Okay.
Okay, I'll show you a few examples after this. Let's look at the in order. Okay, let me get rid of these. So here's in order. In order is LVR. LVR. So when I start from here, it says go left, don't visit it. So we go left.
Okay.
Okay, LVR. Again, we don't visit it, we go left. LVR. It says go left. Now there's no more left.
So
So
we
we
visited.
cross this, and now we go visit this. So the first, which is going to be visited, is 2.
Mm-hmm.
This one doesn't have any right, so we're done. We go back now. When you go back, we've done the
Go left.
Now we visited. So we're going to write 3 over here. Okay. Now we go right. There's a right. So we're going to go over here again, LVR. There's no left. So we visit 7. Okay. There's no right. Okay. So we go back. Now right is done. We go back. Now when we're going back, left is done. We can visit
We
this
visited,
now.
yes.
We're going to get 5. Okay, now
And
we
then
go right.
right.
Okay, when we go right, LVR. 4 has a left. So I'm not going to visit 4. I'll go left.
So we go 1,
So we go 1,
and
then
then
we go back,
and then
visit
we take
4.
it. Then we go
Okay,
to
then we
6.
go right, we go 6. Okay, we go back now. This is done. We go back,
Then
this
we
is
go
done,
back.
and we're finished. So this is in order traversal.
Mm-hmm.
Let's look at post order now. So I'll repeat the same thing with post order. Okay, so starting from here again,
We go left.
LRV, left, right, visit.
Mm-hmm.
So LRV, it says go left, then go right, then visit.
Then visit.
So we go left, LRV. Okay, there is a left, so we go left, LRV. No left, no right, so we visit this. Okay, we're gonna get 2. We're done with this. Now we go back. Okay, now we cannot visit 3. It says go right. So we go right. So again, there is no left, there is no right, so we're gonna visit 7. Then we go back, visit 3. Okay, now we go back. Again, you cannot visit 5 unless you finish visiting the right side. So we go right, LRV. Okay, so again, there's a left, so go 1. Okay, go back to 4. Again, you cannot visit it, there is a right. So we go 6. Then we go back. Okay, we're done with left, we're done with right, so we visit 4. And then we go back, we're done with left, right, and now we can visit 5 and we're done. Here you go. So this is pre-order, in order, and post-order. These are the 3 algorithms which are commonly used for traversing a binary tree.
So, Doctor, isn't it supposed to be the 3 after the 4
Where?
in the last one, post? because we did left, but we should have done right first, then we visit, right?
No, when you see, look, 3. So we go starting from here, 5, 3, 2. You cannot going back now. 3. Okay, there's a right. I cannot write 3 unless I finish with the right. So finish with the right. This one getting 2, 7.
7. Okay.
Now when we go back, we've already finished left and right, and we're going to visit
okay.
3.
And then we go back. Okay.
Yeah, and then you go back and so on. But if this is clear, there are some properties which are very important to remember. Okay, so I'm using the green color to show you this. In pre-order, the root is always the first one.
And then post order is the last one.
Post order, that's the last one. Okay, in order is going to be somewhere in the middle. It's not the first.
Exactly in the middle.
It's not the last. It's somewhere in the middle. It depends on the shape of your tree. So this particular tree, there was exactly 3 nodes on the left, 3 nodes on the right for the root. So that's why it's appearing 3 and 3. But if the shape of the tree looks different, it will look different.
If it's a complete tree, then basically it's in the middle.
Yes, it would be the middle. Now, 2 is the leftmost node. Okay, so in order, 2 is the leftmost. It appears first. Okay, same goes with post order. It is the leftmost. So far, so good?
Yes.
Okay. Last property, third property. The rightmost appears at the end.
Pre-order, yes. For pre-order and in order.
For pre-order and in order, rightmost. So these are some properties you need to remember them. If you're reconstructing the tree, if somebody gives you this information and asks you to reconstruct the tree, then you can use these properties to reconstruct the tree. We'll see about this thing. This is considered an easy and a very hard question to do in the exam. Sometimes we get this question in the final exam.
What to draw the tree, or?
They'll give you the pre-order or in-order traversal and ask you to redraw the tree.
Okay.
Any questions about this? Because I'm going to move on to the next topic now. How do we implement a binary tree?
Yeah.
Okay,
Doctor,
good.
just to make sure, by complete binary tree, it means that each parent has 2 children.
Each parent has 2 children, which means that if you look at the last level, it will look like this. So you get exactly 1 node in level 1, 2 nodes in level 2, 3 nodes, sorry, 4 nodes in level 3, and so on.
Okay.
How do we implement a binary tree now? Right, there's 2 ways to do it. Again, using a link structure or using an array. Okay? So let's try to do the one which is more obvious. Let's try to do the link structure one. So I'm just going to show you this. And we can create a link structure like this. Imagine this is the tree, and we would like to implement this. So now what we have to do is we have to modify the node class. Remember previously the node class was storing the value, teacher value, and we used to store the next variable, which was of type node. In doubly linked list, we used to have the priv and the next. Remember?
Yes.
So we had the priv, we have the next, and we have the integer value. But here, okay, we have to remember 3 things. We have to remember the left, we have to remember the right, and we have to remember the parent in addition to the integer value. So yeah, I mean, every node is storing, in addition to the integer, it's storing 3 variables, 3 pointers: the parent, the left, the right. Does that sound complicated?
Not really, but doctor, we need to have a previous and next also.
Yes. No, there's no next. There is a parent, left, right.
So parent is basically the previous.
So now the basis here is, here's my node.
Then
Okay, we're going to define it like this.
Mm-hmm.
Okay, this is the integer value.
Okay.
This is the node left, node right, and node parent. Okay, this
We
is
have
the
3
binary
pointers.
tree. For the doubly linked list,
We had 2 pointers.
okay, we used to have a node that kind of looked like this.
Mm.
So we had the previous, we had the next, and we had the integer value. Okay.
Yes.
For singular linked list, we used to have a node that looks like this. We have the integer value, and we have the node next.
Yes.
This is for a singular linked list.
Mm-hmm.
Okay. So you can see this thing, the size of the node is increasing.
Yes.
Size of the node is increasing. But again, we're hoping that the runtime for this one, we know that this was O of n, this was also O of n. So we're saying that if we take more memory, if we take more space, and somehow we're guaranteed that the runtime is log of n, okay? So that's a good trade-off.
Okay.
I can use a little bit more space, but if it gives me a much faster runtime, all right, we're going to buy that. Okay, that would be a good solution.
Mm.
Does it make sense now?
Yes.
So
But
that's
we have
what
to put a
we-
condition for the root to not have a parent, right?
Of course, yeah, yes. All right. So let's look at this implementation. This is how they've implemented it. So if you look at this tree, okay, so there's 1, 2, 3, 4, 5 nodes in total. So we're going to have 5 nodes like this. So this is the root node, which is storing B. Notice the root dot parent is always null, must be null. Root dot left is pointing to another node. Okay, it's pointing to another node. This node we're storing A. Okay. A does not have any children, so A dot left is null and A dot right is null. But A dot parent would be
B.
the node which contains B, which is the root.
Mm.
All right, so you can see this thing. There's a lots of connections now. Look at D. D has 2 children and it has a parent. So you can see all of its connections are busy. D, the node that contains D. So I'm just calling it D. So D dot left is node C. D dot right is node E. E dot parent is node D. C dot parent is node D. Okay, and D dot parent is node B. This is the root. So B dot right is node D. Okay, so now you can see this thing. To store only 5 things, 5 integers, or 5 characters, or 5 values, how many pointers you have to make? Every node is having 3 of them. Does that not sound excessive?
Yeah, we just added 1.
Yeah, it
Double
looks
linked.
like lots of pointers. But again, we're willing to take this risk as long as the runtime is big O of n. Sorry, big O of log of n.
Okay.
All right, so this is one solution. We can implement it like this. The other solution is we can implement with the array. Like remember this, the same goes with the array-based implementation. Yeah, the limitations we have with arrays. So if I try to implement like this, there's no limitations to the size of the tree. I can grow it as much as I want. You can insert as many nodes as you want. There's no need for shifting if you decide to remove something. Okay. But here with the array, we have the same problem. If you try to store the tree in an array, okay, that's going to work fine as long as you don't touch things. If you try to insert or remove something, that's going to make life complicated. Right. To store the tree in a simple array like this, okay, it's very simplistic, very easy to understand, but we need to use some special formulas to learn and store information in the array.
To
Okay.
have an order.
So what's the formula? Let's look at the formula. So here's array-based representation of a tree. So we're going to have an array.
Mhm.
The first element we're always going to leave it blank.
Okay.
Okay, why? Because it works very well with the formula.
Okay.
So here's my simple array. Okay, so just for the sake of understanding, let's say this is storing characters. So I'm going to have A, B, C, D, E, F, G, and so on.
So 1 is the root.
So A is my root. The root would always be at position 1.
Mhm.
The root is going to have two children, B and C. So B must be the left one, C must be the right one. Okay, B must be the left one, C must be the right one. And then we're going to have D and E and F and G.
So you always
Okay.
go from left
If you
to
look at
right.
the positions, this is position 1, 2,
2.
3, 4, 5, 6, 7. Okay, so we're going like this. So this is the first one, first level, second level, third level, and 4 on. So it's going to increase. If you look at this, this is 1 node here, 2 nodes here, 4 nodes here, 8 nodes here, and so on.
Mhm.
Okay. Now, if somebody asks you, can you tell me what's the parent of C?
The parent should be A.
What's the parent for a node, let's say C? So what we can do is we can check the position of C.
Mhm.
What's the position of C? Position of C
3.
is 3.
Mhm.
Okay. What I'm going to do is I'm going to divide it by 2.
Okay.
Okay. I'm going to divide it by 2. So position of C is 3. 3 divided by 2 is
1.
1. Integer division.
Yes.
Okay, 1. This means that the parent of C is located at position 1, which is A.
Okay.
What about parent for B?
The same thing.
So position for B is 2. 2 divided by 2 is 1.
Mhm.
Does it make sense to you?
Yes.
Okay, try with something else. Look at the parent for G.
Okay. So 7 divided by 2 is 3.
The 7 divided by 2 is 3.5 or 3. So the parent of C is at position 3. There you go.
Yes.
Okay, so this formula works.
Okay.
So what if you want to find the left child? If I give you a node and I ask you, what's the left child of this node? So what we're going to do is we're going to look at the
It's the one
position.
after it, right?
We're going to look at the position for the parent.
+1.
So for example, left child of C. So position of C is 3.
Okay.
What we're going to do is we're going to multiply it by 2. Okay? So 3 times 2 is 6.
Okay.
The left child of C is at position 6. Does it make sense?
Yes.
Try with a different thing. What's the left child of A?
2.
So position of A is 1. 1 times 2 is 2. It's going to give me 2. Okay, which is B. What's the left child of B? So position of B is 2. 2 times 2 is 4. This means this position 4 is D. Right. Think about the right child. How do we find the right child? So the formula should be
Position multiplied by 2
whatever it is, let's say it's C.
plus
Okay,
1.
multiplied by 2 plus 1.
Yes.
Okay, so 3 times 2 plus 1 is 7. So that will be node that contains G. Position 7, G. Okay, is this clear? So these are the 3 simple formulas. If you know them, we can implement this in the array.
So, Doctor, this is the only implementation of binary trees using an array, or is there like other implementation?
This is the implementation using the array. So if you want to use a single dimension array like what we did, you have to use these formulas.
Okay.
Okay, but it does not always work. Why? what if your tree is like this? What if it's not a complete tree like this? What if I have something over here? Okay, so the position for Z would be 8.
Yes. So if
Okay.
you
What if all of this is empty? There's nothing over here, and we have something here. G dot right. Okay, right side we have something X.
yeah,
What
it
should
would be in
position
position
for this
9.
one? Would that be position 9 or something else?
It shouldn't be position
It
9.
should be 8 only.
No.
It should
This is
be
position 8 is Z.
9, 10, 11. It should be 11.
Are you sure? Look at
12.
the formula.
Should it?
What's the
12.
right child of G according to the formula? Right child of G, position of G is 7. 7 times 2 is 14 plus 1.
15.
Should be 15. Means that you have to extend this array. Okay, so we're going to have 9, 10, 11, 12, 13, 14, 15. I'm going to go and put X over here. What about all of these? Would this stay empty?
Null.
Because there's nothing here.
But you can't put something in a position.
So you have to leave them empty.
Mm.
Okay? So imagine if you have a tree that kind of looks like this.
It will take a lot of time.
Is this a binary tree?
No.
Yes, it is. Because it's less than. or
Remember
equal
what's the definition for binary tree? It can have at most 2
to
children.
2.
So here, each one of them is having 1 child. So what's the problem?
Yeah, it's a binary tree.
It is a binary tree. What's the height of this tree?
1, 2, 3, 4, 5, 6, 7, 8.
So height is 8. Which means what's the maximum number of nodes to the power 8 minus 1, which is how much?
250.
27.
Yes.
255.
Mm-hmm.
Okay, to the power 8 minus 1 is 255. Yeah, I need to store this tree. I need an array of size 255.
Well, you only
But-
need like,
While I need only 8 nodes.
yes.
Okay, so this means my utilization is only 8 out of 255.
Mm.
The rest of the space is wasted. You're not going to use that. Does that look very optimal?
No.
Nope. Okay, so that's a little bit of a problem with binary trees. If you try to store them with an array, they waste of lots and lots of storage. If you try to implement them using the linked structures, okay, space is not a problem. Space is not a problem, and it's more efficient. But it looks a bit more complicated because now you're going to have so many pointers going from left to right or parent to child. So bottom line is we finished with the binary tree. Okay, a binary tree's runtime looks very nice. Okay, it may give you big O of log of n only and only if the complete tree is there. We can implement it using linked structures. We can implement it with arrays. Okay, it can be done both ways, but of course they have their limitations. The linked structure looks a bit complicated, okay, but it's very efficient in terms of storage. And if you implement this thing with arrays, okay, the problem is we may be wasting lots and lots of space, in addition to using the 2 formulas. Remember, the formula in the slide is slightly different from the one that we've studied. Why? Because here they're storing everything on position 0. The way we've done it is easier. Okay, we just waste the first space, just leave it empty, don't use it. This way our formula is going to be easier to work with.